Okay, welcome back everyone. In this video, we're going to wrap up our discussion of work and energy by looking at non-conservative forces. So what we want to try to figure out is how do we factor non-conservative forces into our conservation of energy equations? Because if you remember, we basically said that energy was equal to kinetic plus potential. But how do you deal with something where energy isn't conserved? Okay, so a non-conservative force will change the total mechanical energy of a system. In the case of friction, what that force is doing is it's taking mechanical energy and converting it into thermal or heat energy or waste energy, which eventually leaves the system. Okay, so friction and drag are one good example. And one way that we can write the total amount of work done is that it's the work done by a non-conservative force plus the work by a conservative force, and that's equal to the change in kinetic energy. Put another way, the work done by non-conservative forces like friction is equal to the change in kinetic energy minus the work done by conservative forces. Now remember that work is equal to negative delta U. So we can replace the work done by conservative forces with negative delta U. That negative sign will cancel and give us delta K plus delta U. And most of the time, non-conservative work is equal to 0, in which case delta K plus delta U is equal to delta E, which is 0. And that's conservation of energy. But if it's not, then delta K plus delta U is equal to work non-conservative. So that's a useful equation to have. Okay, let's see an example of this. Okay, so a 2,000 kilogram car starts from rest and coasts down from the top of a driveway that is sloped at an angle of 20 degrees with the horizontal. If an average frictional force of 4,000 newtons impedes the motion of the car, so that's a kinetic friction, find the speed of the car at the bottom of the driveway. Okay, so here's the object, there's the car, we have normal force, we have gravity, and we have friction. Okay, so friction and gravity are going to be the two forces that are doing work here, and we can set up that the total amount of work is equal to the change in kinetic energy. Okay, and so that comes from three things: the work done by the normal force, the work done by gravity, and the work done by friction. That's going to equal delta K. So we can set this up, and first of all we note that as it travels down this driveway, the normal force is not doing any work because it's perpendicular to D. So that's 0. The work done by gravity will be the force of gravity dotted with its displacement. And the work done by friction will be the force of friction dotted with its displacement, which is the same. Change in kinetic will be 1/2 mv final squared minus 0 because it starts from rest. And we hope to find v final. Okay, so force of friction down the incline, we can split up things, and this is going to be mg sine 20 going down the incline. And the distance is 5. And now what we've done is, since we've made sort of the force of gravity parallel to the incline, well, that's parallel to D, so we don't need to take a dot product. And it turns out that FG perpendicular won't do any work. Okay, now we add in the force of friction, and that's going to be negative 4,000, because that's going opposite our displacement. That's times 5. That's equal to 1/2 m v final squared. And we can just plug and chug in this. We can find that v final is 3.68 meters per second. Okay. So if we had started with some initial velocity, we would factor that into this, but this was pretty straightforward. Okay, let's do another quick example. A parachutist of mass 50 kilograms jumps out of a hot air balloon 1,000 meters above the ground and lands on the ground with a speed of 5 meters per second. How much energy was lost to friction during the descent? Okay, so basically what we know is that the work done by non-conservative forces is going to be equal to the change in kinetic energy plus the change in potential energy. Now the change in kinetic is going to be 1/2 m v final squared minus 1/2 m v initial squared, and we just have to assume that v initial is 0. Then delta u is going to be u final, which is 0, minus mgh initial, which is 1,000 meters. So then we can plug and chug this out. So the work done by the non-conservative force of friction, or the energy lost to it, is 1/2 times 50 times 5 squared minus 50, let's round it, gravity to 10, and 1,000. Okay, so 25 times 5 squared is 625. Is that right? Yeah, that's 25 squared. Okay, so we get 25 from this, and then 25 from 5 squared. And this is going to be a lot bigger. 500 times 1,000 is 500,000. So we're talking about a non-conservative force here of about, which does about 499,000 joules of work. So that's quite a lot of work lost to friction. Okay, so now let's back up a second and let's talk about how force is related to a potential energy function. So we need to review a couple of things. First, if the force was constant, we had work is equal to force times displacement. And if it varies, we said that work was equal to the integral of f dx, which is equal to the negative integral of du, or negative delta u if the force is varying. So we can set up this integral right here. The integral of f dx is equal to the integral of negative integral of du. And for math, we know that if we have two integrals that are the same, we know that what's inside must be the same. So this means that f dx must be equal to negative du. Then we solve this. So in other words, the integral of a is equal to the integral of CD. This means that a must be equal to CD, for example. Just random variables I'm picking out. And this tells us that the force is related to the potential energy through F equals negative du dx. And this is a huge equation, so I'm writing it really big. Okay, this is how force is related to potential energy. And if you have a conservative force, then it has a potential energy function related to it. Okay, before we get into that, let's talk about stable equilibrium. Okay, and let's do this in the context of a force that looks like this: F equals negative kx. Okay, so if you think about this, if I'm right here, so here's my u of x, and here's some negative x. If I plop a negative number in for x in this equation, the force is going to push to the left. Okay, so F is going to be negative k times negative xa, if this is negative xa. So that's going to be a positive value, kxa, positive value for that force. Likewise, if I'm over here and I have a positive value for this, we'll call it plus xa, then F is going to be negative k times xa and it will have a negative value for that force. Okay? And if we think about this, F equals negative kx corresponds with U equals 1/2 kx squared. And now you can see how these are related. This is the function U equals a constant times x squared. It's just a parabola. And if I note that f is negative du dx, that means that f is going to be negative 1/2 k times 2x, which is negative kx. So that's where this is coming from, okay? So the other thing to notice about this is that the second derivative of this is going to be something very important to look at, okay? So the second derivative of this graph is going to be positive, which means that this graph is going to be concave up. Okay, notice that the first derivative by itself, just du dx, is going to be kx, and that means that d squared u dx squared is equal to k. So it's a positive, this is concave up, and this is what we call a stable equilibrium. Okay, and this happens whenever there's a force that tends to push a particle back towards zero. Okay, now let's look at an unstable equilibrium, and this could be u is equal to negative 1/2 kx squared. Okay, now this is not what a spring does, because if I put something up near the top of a spring and I nudge it a little bit, I'm going to get a force that's going to be negative du dx, which is equal to kx, which means that when I'm over here, my force will be pushing me away, and when I'm over here, it'll be pushing me away. This is what we call an unstable equilibrium, that the force ends up pushing away from the 0 point. Notice that back here, these forces were pushing inwards towards 0, and here they're pushing out. And this is all because of the shape of the graph. You take the second derivative of this, and you're going to get, well, first of all, just du dx is negative kx. So du dx, d squared u dx squared is negative k, which is concave down, which is going to be unstable. Finally, we can have a neutral equilibrium. Let's say that u is just equal to k. Then the force is negative du dx, which is just 0. I put something down here, and it's just going to stay there. There's going to be no force. So that's a neutral equilibrium. Okay. Now the last thing to point out is that in multiple dimensions, you can take the derivatives of each dimension separately. And this is another math topic that you may not have gotten to just yet. But here's what it would look like. F of r is negative du of r dr. So F, the force in the x direction, would be negative partial u partial x. And this symbol right here is the partial derivative of u with respect to x. That's how we interpret that symbol. And so what I can do is I can perform this operation, taking the partial derivative with respect to each variable. I can do this and I can stick it all together. So in other words, we would say that r by itself is equal to x I hat plus y j hat plus z k hat. And we would say that f is equal to some function, well, sorry, u is actually a potential energy function of x, y, and z. So it's not just u of x anymore, like 1/2 kx squared. It's going to be u of r which is a function of x, y, and z. Okay, now this has a special name, and what we do is we call this, when we take the partial derivative with respect to x, y, and z, we call that the gradient of u. Okay, so this symbol right here is called the gradient. Okay, that's a very important math symbol. And so really what we're saying here is that this force is equal to negative partial u partial x I hat, because that's what fx is, plus negative partial u partial y j hat, plus negative partial u partial z k hat. Okay, so I'm going to show you a real quick example of this, and I'm going to actually skip through this for a moment, but I'll just point out, notice that right here, this is where f would be equal to 0 because du dr would be 0. Okay, so that's kind of, if you have a molecule, this would be kind of the lowest potential energy, and so this length right here is in chemistry what we would call the bond length. Okay, so we're going to skip this example. We're just going to do this example. So we have a potential energy function, okay, u of xy is equal to 3x cubed y minus 7x, and we want to find the force acting at a point xy. So our definition of the force is negative gradient of u. So we're going to take negative partial u partial x I hat plus negative partial u partial y j hat. So let's just write this out. Negative partial u partial x means basically take the function and pretend like y is a constant. Then just do the derivative. So in this case, it would be the negative of 9x squared y minus 7. Okay, so 9x squared y plus 7. Now we'll just go into here. Then negative partial u partial y. This is the same thing, but then we just say treat x like a constant, take the derivative with respect to y. So that would just be 3x cubed, and that's it. Okay, because negative 7x would be like a constant, so it would be like plus 0. So it's just negative 3x cubed. So we put this all together, and our force would be negative 9x squared y plus 7 I hat minus 3x cubed j hat. And that would be our force function. Okay? So one thing to remember is that anytime you have a potential energy function, you can always work backwards to find a force. But the opposite is not always true. If you're given a force, you can't always work backwards to get potential energy. Okay, so that's it for now. We're going to move on to our next unit on momentum when we come back.